It's fair to say I've been somewhat obsessed with this technology we're talking about today for about a year, but I think there's good reason to be excited about eBPF or BPF. eBPF is a Linux kernel technology that allows unprecedented observability and potentially security applications to be developed. It's also fair to say that when it comes to endpoint defense, Linux has trailed behind Windows in terms of the applications available for it. Now, some might say that's because Linux is more secure by default. But as attackers get more sophisticated, the more vulnerable those Linux servers that we deploy into on-premise or in the cloud applications become. And so with eBPF, we have the ability to develop really rich data and potentially defenses using this technology. But in its current state, eBPF is kind of hard to get started with. So I wanted to create a quick video getting you introduced to the eBPF ecosystem and how to get started with it. Let's go. Let's start with some of the confusion around the name of this technology before we go any further, because you're going to hear it referred to interchangeably as eBPF, BPF, and sometimes people might even use the older terms for it, which actually don't even apply anymore. Originally, BPF was short for the Berkeley Packet Filter, which was a syntax and technology that allowed kernel-level filtering of network packets. That's not what eBPF stands for anymore. The technology was then extended to become the extended Berkeley packet filter, and that sometimes was referred to as eBPF. But that's not what we're talking about either. Now we have the eBPF or BPF technologies, and what they refer to is a virtual machine that exists inside the Linux kernel that allows us to hook into syscalls, kernel functions, and network events, and allows us to take action on the data that we extract. So these days, you can refer to this technology as eBPF or BPF, but it's not really the Berkeley packet filter or the extended Berkeley packet filter anymore. As a matter of fact, the name for the thing is just BPF. The letters don't actually stand for anything. So that's pretty weird, but just roll with it. If you've been in our Discord, and by the way, you should be, you'll know that I haven't been able to shut up about this technology for about a year. And that's because it's an exciting technology that exists in the Linux kernel and soon is going to be available in other places. If you've heard about eBPF at all, it's likely that it's been within the context of its most common application, which is in Kubernetes deployments. And while eBPF is great at defending Kubernetes pods by hooking events in the Linux kernel inside those pods, it isn't about Kubernetes, it's about the Linux kernel. And that means any Linux machine that is deployed anywhere can benefit from this technology. It allows for really profound observability and security applications, but as far as I can tell, we're really just scratching the surface with what's possible. That being said, the bad guys know about what's possible with eBPF. In fact, the BPF door rootkit is already around and being used by Chinese APT groups. I really think the best way to explain eBPF and what it is and what it can do is to just dive in and get started with some of the examples of the technology. So we're going to set up our environment to explore eBPF. I'm going to be using a KDE Neon virtual machine, but any Linux VM that you're comfortable in will do just fine. Let's get started. Okay, here I am in my Linux VM, and I have the BCC Git repo up and ready to go. This is the BPF compiler collection, which is a tool that will allow us to not only write some Python programs hooking into eBPF, but it will also install the BPF library bindings for C as well. So this is really the best place to get started. Now, if you're using Ubuntu or other distributions, there are BPF and BCC packages in the repositories, but the problem is that they're old as dirt. And I strongly recommend that you compile them from source like we're going to do here to get the latest and the greatest. The good news is the instructions for compiling them are really easy to follow. So once you're here at BCC, go ahead and clone that down. We'll get our terminal going here, git clone into BCC. Once that's done, you can click on the install.md right here from the repo. And I'm going to be going down to the source because I'm compiling from source and go to the Ubuntu section. I'm on 2204. That's what this version of Neon is based on. So I'm just going to copy this section right here. This is installing all of the compile dependencies that I'll need to actually build the project. So just copy that install line and fire that off. I already have my stuff installed, so we're good to go. The next part is even easier. This install and compile BCC is all of the commands that you need to execute in order to make it happen. If we look at them carefully, you can see what's going on. We've already cloned down BCC, so we can copy just these lines here. We're going to make a build folder. We're going to run cmake, then make install, then do the cmake again for our Python bindings, and then once again make install, and then we're done. Let's go ahead and copy those down. Run these commands, making sure that you have sudo permissions. And this might take a little bit of time. We're compiling a big project from source, but once it's done, we'll be ready to move on. Okay, that took forever, but now that it is done, we can use the BCC library and some really cool BPF utilities to make it clear exactly what this technology is capable of. To get started, I recommend you head over to the BPFTrace repository at iovisor/BPFTrace, and let's head over to the releases. The raw binary is right here in the assets, so we can just copy that link, and then we can sudo wget this, and we'll put it in user local bin. That's what we did, sudo BPFTrace. And don't forget to chmod it. We're going to explain how BPFTrace works because it's one of the most powerful and easy to use tools in the BPF ecosystem. But before we do that, I want to give you a demonstration of what is possible. And to do that, I'm just going to give you a quick one-liner to use with BPFTrace. Okay, here it is. Sudo BPFTrace -e, and then this very long string in single quotes, tracepoint colon syscalls colon sys enter exec ve curlies join args argv, and I'll make sure that this is in the video description so it's easy to get at. Let's run this and see what happens. So right away, it's fairly clear that what's going on is BPFTrace is finding every execution of a binary on the system, and it is joining the array of arguments for that executable and printing it out to the console. So that might seem pretty contrived, but there's actually a lot of work going on under the hood to make this possible. And think about what you can do when you have access to all of the executables and the arguments to them on your Linux system. Here's another one-liner real quick, just so you can see another neat trick of BPFTrace. So here we're going to do kprobe, not tracepoint, TCP connect, and then this weird statement here with @cons com equals count. Let's fire this off and see what happens. Nothing for the moment, but I encourage you to reload some pages through your web browser, maybe use curl someplace, just to see what happens. Okay, and then after a little bit, Control-C that BPFTrace command, and what you get is a listing of all of the TCP connections by the executable that made them. So again, this is a really cool aggregation tool to give you data about what's happening on your system, and it's all being done through eBPF using the BPFTrace scripting utility. So now that you've seen it work, let's talk a little bit about how it works. When we run an eBPF program, we are sending special bytecode to the eBPF virtual machine that is running as part of the Linux kernel. So depending on whatever your tooling happens to be, if it's BCC or some of these other products that are available, or just raw programming languages like C, C++, Rust, or Go, whatever you want to do, you're compiling the program down into eBPF bytecode. That gets run through the verifier and the just-in-time compiler, and then using a few other tools like maps, which we'll talk about, and the kernel helper API, you get information about events in the kernel using what are called probes, trace points, and a few other types of hooks as well. Once you have that information, the information goes back up into user space, and you can do whatever you want with that information. So here's a good example of a small bit of a hook, where we have a process that is executed. When that happens, the execve syscall is called in the Linux kernel. Before anything else happens when we're using eBPF, the eBPF virtual machine gets that information. And if we've written a program that hooks that syscall, that information is passed to us in the eBPF virtual machine. This little snippet of C here is an example of the kinds of things that you can extract out of that event. So here we have an event where we're getting the PID and then the return of that executable. We're also going to use the BPF get current com helper function to get the name of the executable. And then we send that back up into user space through a structure known as a map, which is what that perf submit is all about. And what's cool about BPFTrace is that it's living at a level above the C so that we can write BPFTrace scripts without having to always write C to take advantage of this technology. So for a little bit more visibility into what's going on here, anytime a kernel function is called or a syscall is invoked, we're going to have the ability to hook that with eBPF. But that's not all. Hardware events are also hookable, and really interestingly, network events are hookable. In fact, depending on the network interface that you're using, some of the network events can be processed on the network interface itself using a technology called XDP instead of using the CPU. So there's a lot of really fast filtering that we can do with eBPF. I'm going to spare you writing C today because there is a lot of C that goes on in rich eBPF programs. But to just get started with BPF, BPFTrace is a great way to get started. Let's take a look at the BPFTrace demos as well as some additional tools that I've put together for your exploration. Okay, we're back here at the BPFTrace GitHub repo, and I have to say, even independent of BPFTrace itself, the docs section of the BPFTrace repo is a lifesaver. I strongly recommend checking out the reference guide if you want to just get a gentle introduction into the components of BPF, the probes that you can create. You can see here K probes, U probes, trace points, raw trace points. But now that we have BPFTrace installed, we can use it to learn about what hooks are available for us to write on our specific Linux system. To do that, we can run sudo bpftrace-l. A very long list of potential probes is listed out for us. They have a pretty specific format, and we can even search a little bit more succinctly if we want to just look for all of our trace points, for example. We can use a fuzzy search like this. We can even go more specifically if we want to just look for all syscalls. And here you can start to see the kinds of things that we might be interested in hooking. And this is endpoint stuff, of course, like execve. You might be wondering how BPFTrace is finding all this stuff or how you would know it otherwise. It turns out all of this is listed in your Linux file system. If we sudo ls sys kernel tracing and events, let's see what we see here. Oh, hey, look, here's a bunch of categories of trace points that we may be interested in. And if we go into syscalls, for example, there they are. Now, each one of these is a directory as well. So if we take a look at sys enter execve, there's even more important information here, as we'll find out. But if you are interested in what kinds of hooks your system is capable of, your file system will actually tell you if you know where to look for it. But BPFTrace kind of does that work for us. Now, before going any further, I strongly recommend that you clone down the BPFTrace repository, not because we need to build BPFTrace, we already have the released binary, but because of the tools inside of it. If we go into BPFTrace and tools, there are a ton of .bt files that are BPFTrace scripts. So it's not just for one-liners on the command line, it's a full-out scripting language that allows us to write some really interesting BPF programs. One of the easiest to understand is probably exec-snoop. Let's take a look at exec-snoop. So it's pretty short, and in fact, it's pretty similar to what I was showing you with the one-liner for taking a look at the arguments to an executable. But a couple things to notice here. There are two probes that have been created here. One of them is the begin probe, which is just something that happens at the beginning of every BPF program. There's also an end probe that you can put to end every program. We have a built-in printf function, and we're going to create some columns here. And then we have a hook onto sysEnterExec, either VE or anything else. And we're going to print the time elapsed and then the process ID. We're also going to print out the args.argv. One question you might have is, how would we possibly know that args.argv is available for us? Args are the arguments that are passed to the exec, VE, or other function. So if you wanted to know easily, or somewhat easily, what was available in that function, you have a couple of options. But I think the easiest is probably to use the man pages here, to do man to exec VE. That tells us about the exec VE call. And you can see that one of the arguments is the path name, which is the executable. The second one, though, is argv, which is a pointer to an array of the arguments to the command line. Now that we know that that argument is there, we know that we can access it in BPFTrace. But also, remember all of the files that we saw in the tracing events syscall sysEnterExec VE directory? One of them, called format, is really informative as well. If we cat that out, we will learn about all of the actual arguments that are being sent to the context of that trace point. So this is actually what BPFTrace is getting, or BPF is getting, whenever we hook that syscall. The fields here at the top are unavailable to us, but the ones at the bottom, especially file name, argv, and envp, are available to us. And again, so two ways to understand exactly what's available to us and what shape they are. This file is especially important if you're going to be writing anything in C to take advantage of this probe, because it tells you the size and the offset and, of course, the type of the field. Okay, now that we've explained what this thing does, let's go ahead and run it. You might have noticed that there was a shebang at the top. So we can actually just run sudo./execsnoop.bt, and it will run BPFTrace for us. So very similar to what I was showing you, but with a little bit more formatting with the columns. Control-C will end it. Let's take a look at another one, TCP Connect, which has some really interesting stuff going on with network connections. Okay, again, we see we have a begin probe, and we have some printf statements. Now, this time we're not using a trace point, we're using a kernel probe, TCP Connect. This also really matters because we're hooking the function itself, not a predefined trace point. Now, if we want to know more about the TCP Connect function, the man pages may not help us out here, so we may have to go actually look at the Linux kernel, but it's not as scary as all that. One of my favorite places to do so is elixir.bootlin.com, which has a great breakdown of the Linux kernel. And so we can search for TCP Connect, find that it's defined in one file as a prototype and in one file as a function. That's what we want to see. We want to see the function itself. And we learn that TCP Connect takes one argument, but it's a whopper, which is the sock struct. And we can even click on sock right here to learn more about what that actually is. Defined in 3 files as a struct, we'll want sock.h. And as we can see, there are quite a few fields inside of the socket argument. This takes some practice to get used to, but let's take a look at how the TCP Connect BPFTrace program uses this socket struct. Notice that even before the begin hook, we have some C-like includes, like socket.h, sock.h, and sys/socket.h. Inside of the TCP Connect probe, we're using ad hoc variables, which you can do in BPFTrace, and we're using some C-like syntax to cast the first argument to TCP Connect, arg0, into a struct sock pointer. Now that we have that variable and we've cast it that way, we can access the members of that struct with the arrow syntax. So what we're doing here is we're looking for IPv6 or IPv4. We're getting the L port, the D port, the source address, the dest address, and then we're getting all that ready to print out very cleanly with source, source port, dest, and dest port. And that's really all there is to it if you know how to read those components of the Linux kernel, which is one of the trickiest parts of this. But I want to stress again that BPFTrace is doing a lot of work making the rest of this really easy for us. Let's give it some network traffic. There we go. Let me give it another curl just for good measure. There you go. And Control-C to end it. So this is all cool, but so far we've only been talking about basically observability and system monitoring. How can we use this for some security applications? For that, I've put together a small repository of projects that I'm playing with called BlueBPF. Specifically thinking about defensive applications for BPF, because we know that there are offensive applications. So if you want to play with some of these, you can go ahead and pull these down. I'm going to do that right now. Git clone. And I'm going to head into BlueBPF and look at the BT for the BPFTrace files. There are 4 in here right now. One of them is a keylogger. Now, this is a virtual machine, and I'm RDP'd into it, so I don't have the ability to give it physical key inputs, at least not from here. But I'm going to try from the hypervisor, and we'll see what happens. The keylogger is pretty cool. Using some hackery using maps, which are the built-in databases that you submit and read data to and from, in eBPF, I've put all of the input key codes that I'm interested in as readable values in there. The reason why maps are so important is because the eBPF program stack is only 512 bytes. And so if you want to send really large amounts of data, like a string or something exciting like that, into user space, you have to do it through these maps. Once I have them defined, I hook the input handle event function, and I'm doing a little bit of filtering here to make sure that it is the kind of key press that I care about, and then I'm simply printing it out. I've in comments here put the arguments to this function just so they're clear for me, but I don't actually use this in the program. You can also see that I'm timestamping things, which is kind of nice. So let's try running this. Now, as I press keys on here, it won't log anything. But as I start typing into the hypervisor, it reads them perfectly. So it might be crazy to think of a keylogger as a defensive tool, but depending on how you're monitoring your system, this might actually be super valuable. I won't use Portmon because it's very similar to what we just saw with TCP Connect, but a little bit different output, so you might want to play with that one. I will, however, show you SSHSpy because it's crazy cool. What SSHSpy does is it reads in the data coming into the server on an SSH connection. So if someone is SSH'd into the server that SSHSpy is running on, it's going to show very messily the data that the user is sending. Now you might think, okay, well, SSH is encrypted. How is it doing that? Yes, it is, but let's take a look at what SSHSpy does so that it can reveal all. At some point, the SSHD program has to read from a file descriptor in order to get the contents that have been submitted, and that is what we are hooking. The idea here is that if we're defending and we're on this system and we're root, we're going to use our home field advantage as much as possible, and that means that we can read this thing coming in at some point. We're using maps again to keep a count of how many reads per user ID and file descriptor there are. One of the reasons we're doing that for the file descriptor is that I have found that SSHD almost universally uses file descriptor number 10 to read in user input from all SSH connections. But that's in my experience, and yours may differ. Using this map to file descriptors might help you figure out what file descriptor you should use for this filter here to figure out what you should be hooking and reading to see your SSH communication. Now, again, this is going to be messy when we run this, but the user input will be there. And the reason it's going to be messy is because the SSH connection is not just reading in the text of the input, it is reading all of the terminal display that is being sent. So we have to kind of parse through all of that in order to see what we want to see. Let's run this and you'll get an idea of what I mean. So sudo SSHSpy. Okay. And now I am going to SSH to myself at localhost. And you can see it's very messy, but I'm getting some information in here. Fish is crazy noisy with this, so I'm going to do bash just to kick it over. And now you can see that I am displaying the content that is being sent over the SSH connection using SSHSpy. When I end the connection, I get this list of what file descriptors did the most talking for me. And as you can see, file descriptor 10 was doing a lot. There were others that were more interesting, but in my experience, that wasn't user input. Okay, last demo, and this is definitely my favorite. The ShellGuardian application allows you to monitor for executions of shells, and if a shell is kicked off by a service user, meaning not root and not UID 1000 or above, it will announce it, and if you launch it in kill mode, then it will kill that process right away. One of the reasons I wrote this was thinking about web shells, where they will have to invoke system at some point, but a compromised web server will invoke that as www-data or whatever your web server service account is. This stops that from happening. Now, it's a little bit crude, but it demonstrates what is possible with eBPF. So to start, we're looking for that -k argument to see if we want to start in kill mode, and we save that to the map kill mode so that it's a global variable. We hook execve, not too crazy there. And again, we're just looking for all the possible shells. Bash, fish, zshell, -sh. You could add as many different filters as you want. And we're counting the executions using maps one more time. We're timestamping, and then we're printing out arguments just so that we have some interesting output that you could send to a log if you like. Then we're going to use a kprobe, not a trace point, and we're going to hook all sysexecves. The reason we wanted the kprobe is so that I could use the signal function, which I cannot do when I'm using a trace point. So here I'm just looking for bash executions, but you could filter more interestingly. And also I'm looking for just if kill mode is activated. When that is true, I send sig kill to the process. So let's see this thing in action. Okay. Sudo ShellGuardian. Oh, right. I have to open it with unsafe, and I will also kick it off in kill mode. There we go. So you see all these shells are coming in. That's fine. Now, if I cat etc password on this server, you'll see that I have SSHD as ID 116. That's over 0 and less than 1000. So if I do sudo -u sshd bash, that should break my rule for kill mode. And indeed it does. So you can see here, we got service account shell killing unauthorized shell. Now, if I try to ls in here, it says killed. PWD. PWD is a built-in for the shell, but if I try to do anything else, killed. I can't actually do anything from this shell. At the very end, I'll get counts of executions and counts of shells per user. So if you want to go further with BPFTrace or BPF in general, I strongly recommend starting with the BPFTrace documentation and learning the BPFTrace scripting language. Once you're comfortable there, BCC actually has tools that are mirrors of the BPFTrace tools, but written in Python. And then the Python component has the C program that actually compiles to the eBPF bytecode. And so you're seeing the abstractions that were handled by BPFTrace made explicit with these programs. So for example, if we take a look at exec-snoop here, we see the Python component, but then when we go down, there's just a raw C program built into this thing. And that's really where BPF starts to get a little bit trickier. But again, the BCC documentation is going to be where you go next, because the BCC documentation has a reference guide that is a very clear explanation of all the components, the probes, trace points, and the helper functions that you can use to make eBPF programs. So that's kind of the next step for you. If you really want to go hard mode, there is a Rust implementation of eBPF programming called Aya, but I have to tell you, it's not done yet. It's very much early days for Aya, but there are some really cool tools that have been written with it, including a tool called Kunai. Now, Kunai is like what Sysmon should be on Linux, but isn't. Even though Sysmon for Linux, which is written using eBPF, exists, Kunai goes a little bit further in what it is able to log. And I'm really impressed by this project, and it's also a demonstration of how you can use the Aya Rust eBPF implementation to do some really cool stuff. So I encourage you to check that out. That link will be in the description as well. But that's it for our introduction to eBPF. I hope you're starting to see why I'm so excited by this technology and what you could possibly do with it. I'd love to see the programs that you generate, and maybe I'll see a PR for them in BlueBPF. Until next time, friends, be good to yourselves, be good to each other, and happy hacking.